Hey students, I promised I would work out some examples. So I'm finally getting around to it. A little slower than anticipated. Had some weather-related issues with my roof, but that behind me. Let's go ahead and use the examples that I was going to do in class if we had class. And so I'll just put this on video here, and I'll just make the list right here. 1, 2, 3, 4. Looks like I've got 6 of them in my notes. Usually in class we run out of time, so maybe this is a better approach. I will just be able to do more than what we would have been able to do had we not had class canceled due to weather-related issues. But let me jump right in here. Number 4 is a good one, and I've just got the hard copy of the book right here. So I'll just use the hard copy here and kind of look at them and kind of go back and forth. Let me just give myself a little bit of space on my messy desk here and say, all right, let's go ahead and look at number 4 here. Oops. For beginners. And what does number 4 here say? It says a multiple cylinder gasoline engine in an airplane operates at 2,500 revolutions per minute. It takes in energy of this much and exhausts this much for each revolution of the crankshaft. Okay, so we got to keep in mind that each revolution, and I guess we could figure out how much time that is because we know that there is 2,500 revolutions in 1 minute. So keep that in mind. How many liters of fuel does it consume in 1 hour of operation if the heat of combustion is this large amount of joules per 1 liter of gasoline? Okay, what is the mechanical power output of this engine? Ignore frictions and express in horsepower. Okay, what is the torque? Okay, and then what is the power and the cooling system? Very interesting questions. A lot of mechanical questions. Kind of makes sense. We're kind of building a heat engine, but I'll use this as an opportunity to then point out that we're seeing in this chapter a lot of mechanics, and so our Physics 121 keeps popping in for us. All right, well, let me move that out of the way there and say, all right, so we've got a multiple cylinder engine, and the first part said that it was 2,500 revolutions per minute. Now, maybe I will turn that into 2,500 revolutions per 60 seconds for just a moment and get an idea of how many revolutions I have in a second. And so it looks like 4.1, I'll just call it 67 revolutions in 1 second. Because a lot of this asked me about the rate here, if you will. And where I'm going with this is, then it said, and if I kind of build a little picture here of my engine, it says energy is coming in to my heat engine. And let's see. It takes in 7.89 times 10 to the 3rd joules for 1 revolution. So I'll go per revolution. And of course, as we talked about then, the engine is designed to send out some work, but also because of entropy, and I don't think entropy is going to be part of this question, but I'll just kind of put it in my diagram. And since entropy has nothing to do with work, this was our second law of thermodynamics saying that you've got to have the entropy now leave the engine so we can get the engine back in its original starting point, because entropy is a state function. And so to get it back in its starting point, we've got to get rid of that entropy. So we've got to get just as much entropy out as went in. And fortunately, entropy can be more concentrated at a lower temperature, so we could actually get the same entropy out at a lower temperature and therefore less energy. And so we have a little bit of energy left over from work. And so the work done using conservation of energy must be the difference between these two. Now, the problem says, let's see, and it exhausts 4.58 times 10 to the third joules. And that would again be per revolution. Okay, so this, like I said, is our idea of operating the engine. Now, the first one, it says, how many liters does it consume in 1 hour? So I guess I would start with it. It's got to get this much energy. And so it's 4.89 times 10 to the third joules in 1 revolution. And keeping that in mind by multiplying it by 2,500 revolutions per minute, this would tell me how much, of course, energy is going in 1 minute. So each revolution, and there's 2,500 revolutions. So if I then go 60 minutes in 1 hour, I would then have how many joules are going into my engine in 1 hour, because revolutions would cancel, minutes would cancel, and so now I got joules per hour. And then finally, the important thing here is that 1 liter of fuel is worth 4.03 times 10 to the 7th joules of heat. And so the joules would cancel off, and I would be left with liters per hour. And that's perfect. All right, and that's the first question. Let me just double check. How many liters of fuel does it consume in 1 hour of operation if the heat of combustion is? Okay. So grabbing my calculator here, I will go the 7.89 times 10 to the third, multiply by 2,500, multiply by another 60, then divide by 4.03 times 10 to the 7th. And it looks like about 29.4 liters per hour is our consumption rate of this plane. Okay, and so if I was a pilot or engineer here and trying to figure out this operation, this is what we need to account for. 1 hour of flight, it's going to be roughly 30 liters. So make sure we have enough fuel to get wherever we're going. Then it says, what is the mechanical power output of this engine? So this comes back to what I was saying earlier. This then would be the work, the difference between the energy going in and the energy going out. And remember, this is the energy in 1 revolution. Okay. So the amount of work in 1 revolution, and I'll just put the power of 10s to the outside, would be 7.89 minus 4.58. And we're looking at about 3.31 times 10 to the third joules per revolution is the work. Now, if we multiply that by the number we got here at the very beginning, 41.67, revolutions per second. The revolutions will cancel off, and we'll get the number of joules per second, which is power in watts. And so that's what they say. What is the mechanical power output of this engine? It says we can ignore friction now, and then it says go on to express it in horsepower. So I guess we'll do a little bit more here, but let me just get it in watts here for a second. So let's see. 3.31 times 1,000, and then times 41.67. Okay, so this would be a 1.379. I think I'll do that. 1.379. 1, 2, 3, 4, 5 times 10 to the 5 watts. Okay, so about 137,900 watts. Now, the last step for B, taking us back to Physics 121, is, what is a horsepower? And so a horsepower is kind of this idea developed by, I guess, James Watt when he's trying to sell his steam engine. And he said, well, a horse working all day averages 1 horsepower. So short term, a horse could do a lot more than 1 horsepower. But if you took a horse and took what it can do in one day and divided it by the 24 hours, that's what a horsepower is. And a horse has to sleep. So a horse actually is always working more than 1 horsepower while it's working, because then it's resting, which is doing 0 horsepower. And so averages 1 horsepower for the day. But it's 746 watts. Of course, for you guys going into mechanical engineering, this gets even more interesting, because then there is electrical horsepower versus mechanical horsepower versus braking horsepower. But on average, let's just call it the 746. So if I divide that by 746 watts, we're looking at about 184.9 horsepower. So there's the horsepower of our engine here. Like it's a gasoline engine, so probably a small little Cessna type of plane. Keep going. There was a C, which C said, what is the torque exerted by the crankshaft on all the load? Okay, well, maybe torque times angular speed, which is power, needs to be reminded of ourselves. Maybe you can see it here. Power is the rate at which work is being done per time. Work could be thought of as a force times a distance, but in terms of angular stuff, torque and an angle is the best way to kind of think of it. And then when you take its derivative, you get torque, and then how the angle changes with time, which is its angular speed. So that's where that came from. I know that in 121, we did a lot of power and linear motion, so force times velocity, and so this is its rotational equivalent. So that would mean the torque from the engine is power divided by its angular speed. All right, so with that in mind, we have the power from the part B, and let me do that in the watts. So this is the 1.379 times 10 to the 5 joules per second. And then the angular speed, which we know to be 4.67 revolutions per second. Let me multiply that by the 2 pi radians per revolution to make the units come out right, because we're going to see that revolutions cancel off. And I'll just remind you that a radian is not a unit, it's a clarifier, since the definition of a radian is the arc length over the radius, and so you got meters over meters, let's say, so it's unitless. And so we often throw in the word radians to distinguish it from degrees, but it again is unitless. That's really nice, because then, as I look at my units here, in the top would be joule per second. Down here would just be per second here, which would cancel off. And that would be left with a joule, but of course the unit is a Newton meter, and then our little discussion back in Physics 121, you should always write torque as a Newton meter, never as a joule, otherwise people might think you're talking about energy. And so we always put it in a Newton meter. So perfect, the units come out to what I had hoped, which are a Newton meter for our torque. So putting in our numbers here, 1.379 times 10 to the 5th divided by the 41.67 divided by the 2 and also divided by the pi. Give me a torque, and a nice big torque of 527 Newton meters. So this plane's designed with a lot of torque and very little horsepower, and that makes sense. You're trying to chop this blade through the air, and it's not an issue of power per se. In fact, we probably want to keep the power on the low side. That way we don't have to have a gearbox out, and we can keep the RPMs down on the low side. That gives us the more torque for the small amount of power. And so there's always that interplay between torque and power. And you know, especially like in a truck, whatnot, you want a lot of torque at a low RPM so you can pull that trailer, unlike a car where you can usually get a lot of torque but on the high end at RPMs. And good sales tactic is to list the high torque at like 4,000, 5,000 RPMs, but you know, how often are you really driving your car at that level? All right, well, let's finish up this problem. D here, it says, what power must the exhaust and cooling system transfer out of the engine? Well, we kind of touched on that back here when we said this is coming out at a rate, that is, the heat energy is coming out at a rate of 4.58 times 10 to the 3 joules per revolution. And then if you multiplied that by the 41.67 revolutions per second, you would get the rate per second. That's watts, or joules per second. That's watts. And so this is the rate of energy coming out of our system. And that's what they're asking. The exhaust system and the cooling system must transfer this out. And in most engines, it's about a 50-50 of what comes out. Half of the heat comes out through the tailpipe and the exhaust, and the other half is brought out by the water in the cooling system. And so 4.58 times 10 to the 3 multiplied then by the 41.67 gives me a rate of 1 point, and I'll just call it 91 times 10 to the, oops, it's got to be a 5, doesn't it? 1, 2, 3, 4, 5. Yeah, 10 to the 5 joules per second. So going back to A or B, well, both A. I guess we didn't calculate that per second, but this is then the rate of mechanical energy, and a little bit more. Let's see, 4.5 doubled is 9. Yeah. So a little bit more percentage-wise, heat is coming out than heat went in. So the work is not quite half the energy. And so this is about a 1.4, and this is about a 1.9. And so the heat coming out. And they just say at what rate. They don't really say what units, and so I'll leave it in watts and call this a good first example. All right. Hope that helps, and in fact, maybe I'll break these examples into separate videos so I don't have just one big long one. Take care.